Good afternoon, everyone. It's been an honor for me to be here among all the scientists. And today, my name is, as mentioned by Professor, that my name is Djeane Debora Onthoni. You can call me Jen. And I work in National Health Research Institutes in Taiwan. Especially, we are working under the department, the Institute of Population Health Sciences. And today, my talk will be related to deep learning-based multimodal diabetes classification using UK Biobank Carotid Ultrasound in association with CVD. So today, we are going to see some of the outlines, such as introduction, the motivation of my work, and the goal, the proposed idea of our work, and the results, and finally, the conclusion and Q&A. So our work basically related to the diabetes mellitus, where, as we know, this kind of disease is chronic kind of disease, and it's affecting 42 million people worldwide. And diabetes mellitus promotes the development of atherosclerosis. If we see more detail about atherosclerosis, it's a plaque formed in the arteries. I think many clinicians familiar with this type of event, and it can cause our vessel narrow, and then it can reduce the blood flow, and eventually it may lead to the high risk of cardiovascular disease. And normally in the practice, the doctor to observe this atherosclerosis, normally they will go for the carotid ultrasound. So they will use this type of image to check whether the patient has this kind of incident. And this is one of the picture I just put from the UK Biobank. And as we can see here, normally they will go for the measurement which called CIMT, or carotid intima media thickness. They will measure it, and then they will know whether this patient has atherosclerosis or not. So CIMT is very important biomarker, and it's measured by the expert. And we can see that CIMT has the association between the CVD and also diabetes patient. Here I have summarized the association between CVD and diabetes case if we consider the CIMT. As we can see here, in the CVD, this kind of method is non-invasive technique because it's from the carotid ultrasound. And in CVD, CIMT is used for the early detection of the atherosclerosis. And in diabetes, it is actually linked, when patient has a diabetes, is linked to accelerate atherosclerosis. And in CVD, this CIMT actually mentioned as a surrogate marker for CVD, especially in the diabetic patient. And it has been reported that CIMT demonstrates significant association with diabetes, and for individual with diabetes exhibit higher CIMT compared to healthy population. So this is how this CIMT related to the diabetes and also CVD patient. The motivation of our work is actually based on the conventional diabetes mellitus predictor, such as age, sex, BMI, and also CIMT itself, where may not sufficient for the comprehensive assessment of the diabetes association with CVD. And it has been reported that there is an association between diabetes and carotid ultrasound parameters such as CIMT and carotid plaque characteristic. And however, CIMT itself contains a measurement of the thickness. It doesn't contain the characteristic of the carotid artery. Therefore, based on this list of the motivation, how can we directly utilize the carotid ultrasound to improve the assessment, particularly in classifying diabetes associated with CVD? And second motivation is that we try to check the literature, like whether they have used imaging particularly to develop the diabetes mellitus prediction. And so far, we found there is one work where they use ultrasound fetal cardiac image for different type of diabetes. And another interesting work that they have used numerical data and they convert into image format. And as we can see, they use two steps, where first they use the feature extraction, then they go for the classifier for the diabetes prediction. However, we found that lack investigation on whether carotid ultrasound can be directly used as an imaging biomarker to classify the patient with diabetes or without diabetes, and it's associated with the CVD. So this is our second motivation. Based on these two motivations, our goal, we want to investigate whether the carotid ultrasound in conjunction with conventional predictors such as age, sex, CIMT, and BMI can improve the performance of classification diabetes associated with the CVD. And to achieve the goal of our work, we propose a deep learning-based multimodal diabetes classification. We have used the UK Biobank, particularly carotid ultrasound image, and it's associated with the CVD. So we can summarize our contribution. First, we have designed and customized a simple yet efficient CNN model where it can extract the features from the image, which can provide the information for diabetes and non-diabetes patients. Secondly, we aggregate the features derived from the model, and we combine with the scalar feature, such as BMI, age, sex, and then the CIMT. And then we develop the multimodal classification using the logistic regression model. And the third contribution, we also analyzed statistically whether the diabetes probability, which is we have designed earlier from the CNN model, can have a positive signal towards the CVD outcomes. So this is basically our contribution. And before we will see how the framework of our work, I would like to introduce the data, like how many data we have used for our experiment. As we can see from the table, we have used the carotid ultrasound from the UK Biobank, and then we have considered the patient who has the image and also the scalar data. They are around 17,402, and then we consider some cases for diabetes and also non-diabetes, where the status of this diabetes we actually got from the UK Biobank data coding. They have a code which can define whether the patient has diabetes or not. So based on the data, we define the patient who has diabetes and non-diabetes. And as we can see here, the diabetes case is quite less if in comparison to the non-diabetes. So we formed two different control. First is the control match, and the second is control random. So for the control match, we match with the age and also with the gender. And the training and testing ratio, we just use 80:20 for our model. So this is the overall of our proposed idea, where, as we can see, first of all, the image from UK Biobank is not ready to be used or to be fit in a CNN, so we have to pre-process them. Luckily, for UK Biobank from Stanford, they have proposed the pre-processing, which is we can access through their GitHub, and we actually use their method to pre-process the image. And after we got the pre-processed image, then we fit into the CNN, and with the CNN, we fit the training, which is from the case and the control match. And after that, we go for the validation. And then, finally, at the end, we form the multimodal, where the features, which is directly learned from this, we fit and we concatenate with the age, sex, and also with the BMI. And then we form them as a whole features. Then we apply logistic regression, and then we predict whether the patient has a diabetes or non-diabetes. So this is the overall of our proposed idea. And if we want to see in detail how we construct the CNN architecture, it's actually simple but yet efficient, we name it that way. So it actually only consists of one convolution layer. And we also have based on our experimental, we decided these hyperparameters. And then in total, from the image, we have the total features is around 1024. So this feature will be concatenated with the scalar features. So based on our model, we try to do some combination, like within the scalar and image, and we try to see whether image has a potential predictor, it has an effect on the prediction. So as we can see here, when we only train the model simply using logistic regression, if we only use age and sex, the average performance is around 0.683. But when we added the image features, where from 1024 plus 2 features from the age and the sex, we got increasing performance in average around 0.728. Similarly, this type of pattern we found when we try to add another scalar features, such as CIMT and also BMI. So we found that, we observed that image features actually has a predicted power when we combine with the scalar data. And we also try to see how in RLC curve, how the model is actually predict the positive, the DM and non-DM prediction, a class. As we can see here, the A figure is only using the age and sex and the image features. And B, we have added the CIMT value. And C, we have added the age, sex, CIMT, and also the BMI features. And we found that the AUC value using the image with other scalar features, it has around 0.67. So this is another evidence that the image features is important to be considered in diabetes and non-diabetes prediction model. And here another interesting thing we try to see is that we want to visualize how actually the features which contribute to the diabetes and non-diabetes prediction model. So we try to calculate the correct activation within the CNN, and here we can visualize them. And on the first row is actually the feature created for the correct class, which is the non-diabetes class. As we can see here, we found a same pattern within the correct class. Here, in the non-diabetes case, the color like more into yellow is like more important. As we can see, it's showing in the wall of the carotid artery, as we can see over here. Meanwhile, in the diabetes class, it's quite interesting that in diabetes class, the important part showing is actually in the lumen area, means that is in the carotid area itself. So this kind of pattern we found in control match and also the control random, which we have defined earlier. And we also try to see how about we compare our model with other existing state-of-the-art classification, such as VG16 and ResNet, and we still found that our model still outperform with others' architecture. And this is the other important part of our work, where we try to analyze statistically whether the probability from our model can have a signal, positive signal towards the CVD status. So we have designed a simple logistic regression where we use the CVD status, we extract from the EHR data, we define them, and we design it into two cohorts. The first one, in the respective way, we try to track the patient 5 years before the image taken. And then we also design the prospective way where we track the patient from this case where non-diabetes and what happened with 843 patients after 3 years after the image has taken. And we found that the probability derived from the diabetes mellitus prediction, it has significant association with the CVD status, and we found specifically only showing in the left side of the carotid artery. So we have two carotid artery, and we found it's more significant on the left side. So this is very interesting what we found during our experimental. And that's all what we have done, and the contribution of our work. We have designed the multimodal diabetes prediction model in associate with CVD, and we actually believe that image such as carotid artery has a predicted power for complex disease such as diabetes. And we also believe not only carotid artery, maybe there are a lot of medical imaging which can be analyzed, which can be correlate with other kind of data. Like I heard today, like in this conference, a lot of genomic related data. We thought that image also can be linked to the genomic data to find some positive sign about special disease, cancer or complex disease. So this is our work. And we would like to thank for the UK Biobank study, and this study is under the application number as shown in the slide. And this is just the reference of our work we have cited, and these are, I thank for my PI and all my deep learning team from my NHRI office and our Institute Population Health and Science. And thank you so much for all of your attention. And if any question, please feel free to ask. Thank you.
Okay, yeah, sure. So, Jason, you want?
Oh,
question?
okay, sure.
Okay, thank you for the very interesting talk. So I have several questions. Shall we first go back to the data set we have? Yeah, great. Thanks. So here, our training and testing is both based on the undersampling to balance the distribution, right?
Yes.
Yeah, but like for the real life, we always know like the case and control cannot be balanced. So I think the reasonable thing is like you can make your training set be balanced, but why like you control your testing set? You make the testing set also in the like this balanced data distribution.
Oh, thank you for your question. So we would like to train the model using the training balance, and also especially not training actually, I mean to say the case to be balanced and also the controls to be balanced, because we thought it's for the classification task. So it will be better to consider the balanced class so that when we want to evaluate the metrics, it will be good to calculate them, and it's more reasonable for the performance evaluation. For that purpose, we make it as a balance.
Yeah, I mean, I understand the training set, so you can always like balance your training set.
Yeah.
But like normally, we should have the exception. We don't have any information on the testing set, right?
Yeah. We actually separate them.
Yeah, I know. But like we
Yes.
still like first downsampling the distribution for the whole set.
Yes.
So it's already have like a prior distribution on the testing set. So that's my question. Have you like tried to testing on the other, because we have like after the downsampling we got this about like 2,000 training testing, right? So we have another 10,000 more we are not using. Have you testing your model on that things?
Yes, that's a good point. Actually, we after we resample, we actually also done another experimental with maybe other kind of control. Like we try to utilize this data. Yes, but for this for this result, I have presented the one which we have sampling, but we actually plan to do it with the other rest of the control case. Yeah.
Yeah. And then shall we go to the model?
Oh, sure.
Thanks.
Is it this?
Yeah, so I was wondering, is it end-to-end training process, or you like first do the unsupervised on the CN, then do the logistic regression, or the? Because I'm a little bit confused here.
Okay. Do you maybe you see that it looks like a two kind of things, right? So actually, this is in experimental point of view. This is executed in a one at a time. So when first we train the model using this CNN, so after the training is finished, then when we go for the testing, we use that the same workflow, and then at the end of the pipeline, we actually here in the CNN, we do not have the last layer for the prediction purpose. We just use the features. So that features is passing through we concatenate with the scalar data, then those pass to the logistic regression in that way.
Okay, so it means that basically.
Okay, so I think there's any more
sorry.
questions? Because
Sorry.
your question is a bit technical, so maybe we can do it offline.
Yeah.
We can have the discussion after this.
Okay.
Sure.
Sorry.
Because of time constraint.
Thank you.
Thanks for the nice presentation. Can you turn to the slide, show the performance of the different models? Yes, I think before this one.
Oh.
Yeah.
Before
this.
Okay.
Yeah, here. So I see the models that the image plus age and sex, and compare with the image, age, sex, and CIMT. Actually,
Yes.
the CIMT, since the fourth model, actually slightly worse performance compared to the second one. Do you have comments on that?
Pardon me?
Your fourth model with the CIMT.
This one?
Fourth, the next one. Yeah, is 0.707.
Yes.
The second one is 0.728, but with the CIMT feature, actually the performance is slightly worse.
I see. Do you mean this?
Yeah.
Which
Compared to the second one?
Compared to okay. The average.
Yeah, the last column.
Yes. This one and this one, is it?
Yeah, it's slightly worse.
Yes.
But with the extra CIMT feature.
Yes. We actually found in that when we add the CIMT in comparison age only with sex, it has much better if we only add age and sex. But here we actually more concentrate like age, sex, and CIMT versus image, age, sex, CIMT. But the point you raise is a good point that it's actually worse if we didn't use the CIMT. But we more concerned like whether using image, without image, the performance in average has improved or no. In that way, actually, we try to analyze the performance.